Okay, so we're recording. Hello and welcome to the New York City Category Theory Seminar. Today is the last meeting of the fall, 2023, and we are honored to have Charlotte Aten talk about a categorical semantics for neural networks. Take it away.
Well, thanks so much for having me. Yeah, I'm required to
The
provide certain
corpus of
information.
information, right. So where
And
you were born?
so I was born in Rochester, New York.
Oh, wow.
Uh, I was specifically born in Strong Hospital, right across the street from the University of Rochester, where I received both my bachelor's and PhD in mathematics. So it's a long journey uh, to get there.
Yeah.
Uh, so
And
I'm
you're
current.
now in Denver.
Well, at this very moment, I'm in King's College in Cambridge, but I am in the general sense in Denver, in that I am a postdoc at the University of Denver right now. Uh,
Right.
so
Very nice,
yeah.
Charlotte. Whenever you want, we'll welcome you back to New York State. You've traveled the world, but we'll take you back.
Yeah,
Okay,
yeah, absolutely. I'm on the job market right now, so who knows where I'll be next year.
okay,
Um, Okay,
okay,
so yeah, today I'd like to talk about categorical semantics for neural nets. And thank you, Nosan, for giving the suggestion to, use the word. Well, I think you said functorial semantics, but I suppose either way. This is actually something I've been thinking about for a while, which is why I wanted to give a talk for the category theory seminar. And as it happened, I had um, it was a real talk, but in some ways a bit of a test run. It was my first version of this that I gave for the Cambridge Computer Labs Logic and Semantics seminar just earlier this month. And so now I'm going to have a slightly updated version to give to you. So just for a general outline, I'm going to start off by talking about this notion of a discrete neural net, which is this project for which you can find a preprint already on the archive. And then I'm going to use that I'm going to use that to both give some general background about neural nets in case you're unfamiliar. And I'm also going to use that to motivate this more theoretical project, which I'm now really just starting, but I'd like to share the idea since that's already somewhat involved to begin with. And so I'm going to talk about multi-categories, which were, my first idea as far as how to actually categorify this notion in a way that was useful or reasonable. And then I'll talk about how, in that context, we can view neural nets as actually a certain kind of functor. And then I'll talk about something which is in response to some very helpful questions or comments that people had here at Cambridge, which is that maybe multi-categories are close, but not exactly what you'd want. And so I'll talk about one possible candidate for what the truly correct definition will be and make some comments about the advantages of that. And then if I have time, I'll talk about this notion of mathematical structure that I looked at in my PhD thesis and how you might be able to use that to produce some kind of learning algorithm for a very wide variety of possible applications. Okay. So just to start off with, probably most people here are at least somewhat familiar with the idea that neural nets are this biologically inspired framework for developing machine learning algorithms. And usually the things that people think about the most are like gradient descent, for instance, but I'm just going to take kind of a broad view of a neural net as being this biologically inspired thing, and somehow we're modifying it in order to try to have it learn something the way a brain would learn something. So for instance, we might want to make a tool that takes 3 digits as input and outputs their sum without explicitly coding such a function. Of course, that's kind of a silly example, but that silly example should be sufficient for illustrating what it is that I want to say. So maybe at this time, let me experiment with using the whiteboard and seeing if I can get that to that to show up for me. Let's see if I tap around, are we going to be able to? Okay, well, now that, oh, okay, there it goes. Okay, so if I try to switch here, let's see, will I actually be able to share a whiteboard? They have made it a lot more steps than it used to be. Okay, so well, let's see. Okay, so then, oh, of course it can't be that simple. Let's see, I do seem to have a writing tool here. All right, this does not seem to be cooperating with me either. That's what I get for trying something new in real time. All right, so I'm just gonna have the slides. Apologies. I guess that's what I get for dreaming. Okay, so anyway, well, I guess I'll just ask you to imagine, as you probably can, that we'd maybe like to take a few digits like 0, 1, and 2 and add them together to get 6, and then output perhaps 0, 6 as the digits of that number, or 5, 5, and 5, and output 1 and 5 for 15, and so on and so forth. And so, of course, if we wanted to, we could think of having some input nodes, like maybe this x1, x2, or x3, into which we're going to plug our digits. And then, well, we have to do something with them once we plug them in. So we might imagine that we have some f1 that's a function which eats the digits plugged into x1 and x2 and outputs perhaps the digit in the tens place. And similarly in f2, which eats the digits plugged into this x2 and x3 and spits out the digit in the ones place. Now, in this particular application, of course, there is a serious flaw with this plan because adding numbers doesn't really work in this way, but we can imagine that we could do something like that. Or if we're not happy, we could make something perhaps even more complicated where F1 and F2 have their outputs fed into some further nodes, which each carry their own function that takes those values and does something else to them, and then so on and so forth. And at the end, as long as we have two things at this final layer that we're looking at this last output, then, at this final layer, the furthest to the right, then we can imagine that those are giving us, perhaps H1 is giving us the digit in the tens place and H2 is giving us the digit in the ones place. So we could come up with some kind of scheme like this if we wanted to. And we think of this whole assemblage of these 3 slots that we can plug numbers into and these various nodes that each carry, or neurons, if you will, that each carry these functions as being some kind of network of neurons, which is supposed to model the following composite function, which is described here. And so, for instance, the first part of this says take the digits plugged into x1 and x2 and plug those into f1 and then plug that into g1 and then plug that into h1. And that's your first thing that you get out. And then you also get out something else, which is built in a more complicated fashion, but according to the diagram below. So that's the general picture. But of course, just this by itself isn't really enough to model the function we want or to be said to be learning. So, well, what do we actually choose for the activation functions? I said just choose some functions, but of course that's the rub, right? What do we actually choose? So if we made really good choices in the sense of making choices that would actually model the thing that we wanted to model, and we did that ourselves manually, then we'd basically be writing that function, which is more like coding than machine learning, and that's not really what we're trying to do here. We decided we would be too lazy to write this function by hand. On the other hand, if we just choose arbitrary functions, then we almost certainly, and you can even formalize that in various settings if you'd like with probability 0, you can say that we'll actually choose the well, in many settings with probability 0, we'll actually choose the function we want. Maybe in a finite discrete setting, we have some chance, but it's still very low. So we're probably not going to get a function that takes 3 digits and gives us the digits of their sum. That's unlikely to happen just by making arbitrary choices. Okay. So, well, what does learning mean? Learning then means make some choices of what activation functions you'll start with, perhaps somehow arbitrarily or randomly, and then start tweaking those activation functions somehow, or start changing this neural net somehow in order to improve the empirical correctness of the neural net, or in other words, to use some testing data or some training data that you already have that say we know that 5, 5, and 5 should give us the digits 1 and 5 for 15, or 1, 2, and 3 should give us the digits, 0, 6 for 6, or something else of that nature. We might not give it all possible examples, but just some, and use those to determine if our little tweaks to this system are giving us something that's better than before or not. And so there are various ways of doing this, as people know. Gradient descent in a nice smooth setting is what you want to do, or other variations along that general theme. And a lot of work has been done in that direction. But even in cases where we do have good algorithms, there's a different problem, which is overfitting. So as you all know, if you actually try to implement some of these things, it's very easy to train a neural net to do something like perfectly map 1, 2, 3 to 0, 6, 0, 3, 5 to 0, 8, and even 2, 2, 3 to 0, 7. Perhaps all of those examples it can do perfectly, but still totally fail to map 3, 4, 5 to 1, 2. And that's just basically because, people tend to anthropomorphize these things, but based on the general paradigm that I just described and what we usually do, there's no particular reason why this thing should care or be able to generalize from those specific examples to what we think of as the natural thing of adding the numbers and then giving their digits. As long as it's doing perfectly at the task to which it was assigned, it doesn't really care in some sense about doing what we would make sense for the other possible values. And so, often neural nets just take on whatever values outside of their training examples. If you train them long enough to get them to do perfect on their training data, then often they fail completely on everything else. So there are various methods for stopping this from happening, and this first sentence is actually not meant to be completely tautological. There are ways of at least preventing this from happening, if not stopping it, that don't actually make it impossible. For example, people will sometimes take the original data and make it fuzzy. So for instance, if we had training data that said 1, 2, 3 should get sent to 0, 6. Maybe one way of dealing with this would be to say, well, let's actually generate a bunch of possible training examples, which say 1.1 and 2.1 and 3.1 should get sent to 0, 6.4 or something as well. And we just kind of fuzzify the data a little bit, and we might be able to get this to perform a little bit better. And there are other techniques as well. But what I'd like to talk about is a structural approach where we deal with this problem of overfitting by actually restricting the space of possible functions that can be used to build our neural net in the first place, so that it's not possible for certain types of overfitting to occur at least. So for instance, if we just chose all of our activation functions to be linear functions, then our neural net could only model linear functions, because if you plug linear functions into other linear functions, then you'll just get another linear function, perhaps with more variables. So if we were to do this, then we wouldn't be able to overfit at least to using any function that was not linear, because we wouldn't be able to get our neural net to model anything that was not linear. And so what I'd like to do is try to exploit this principle as much as possible. So in general, we can imagine having an object S in some category with finite products and take our activation functions to be morphisms from the n-fold product of S with itself, or its nth Cartesian power, back to S again for various values of n. This collection of morphisms is called the polymorphism clone of S, and it's closed under composition. Okay, I guess if I was going to be really careful, I might say that, like, classically a clone was supposed to be a set of actual n-ary operations for various n, and this could just be morphisms in an arbitrary category with finite products, but it's the same story. So okay, well, if we choose S to be some thing that's relevant to our learning task, then our neural net will only be able to have activation functions, which are polymorphisms, as they're called, of S. And so those would be the only reasonable functions that could be learned by such a system. And so reasonable, again, is our choice, depending on what we think is the correct thing to choose for the problem. It's not, something that's necessarily like inherently given to us by nature. So for instance, actually this whole paradigm encompasses the idea of doing equivariant neural nets, because if we take that object S to be a G set for some group G, so think perhaps RK with the orthogonal group acting on it, for instance, then we can ask that our activation functions for our neural net are not just some arbitrary continuous maps defined on Euclidean space, but are actually ones that commute with the action of that group, in the sense that for each group element sigma, you can either apply it to each of the arguments of one of these activation functions and then apply the activation function, or you can plug all of those things into this activation function that's called F here, and then apply sigma. You'll get the same result either way. Having that property is exactly the same thing as asking that all of your activation functions are polymorphisms of the G set S in the category, like viewed in the category of G sets. Okay, so, well, that's nice, at least, that that's included in this paradigm. And the general observation suggests that neural nets have some kind of nice functorial description. And so what I originally said, although I think I will ultimately modify that in some way for the actual paper, something along the lines of multicategories are what I would like to use. And so I'll give some background about multicategories and then explain why I'm not entirely satisfied with them now. But the general point is just that when we look at the kind of pictures I was drawing before, that seems very reminiscent of the kind of diagrams that we draw for composing morphisms in something like a multicategory. So one way that I might view this picture as being a little more categorical, and apologies if you're familiar with string diagrams in the maybe more conventional way where the objects are the strings and the morphisms are the things that get the boxes. But we can imagine labeling each of these nodes in the neural net with an object in some category, or something like a category in the traditional sense. And we can think of each of these activation functions as being like a morphism that takes multiple inputs but only has a single output. So for instance, this F1 is actually taking something from the object A1, something from the object A2, and it's giving us a thing of type B1, and so on and so forth. And so this is just a slight change in perspective. And this motivates using at least something along the lines of a multicategory. So a multicategory has objects, just like a category usually does. And for each tuple of objects, A1 through AN, and each object B, there is a Hom set, the morphisms of C, which go from the tuple A1 through AN to B. And for each object, there's also an identity morphism, which sends okay, if we're going to be pedantic, the list with a single entry, A to A. And there's a generalized law of composition from which we can form morphisms like G with F1 and or G2 with F1 and F2 plugged into it, like in this picture. So this picture, if I go back to it, is indicating that, say, G2 should actually be having F1 and F2 plugged into its two arguments, respectively. And so, well, in addition to having that data, a multi-category also has to satisfy analogous axioms to those that a category normally has to satisfy, which is that we have some, in this case, generalized associative law that I don't care to write down, and identity laws, which say if you plug in the appropriate identity morphisms into all of the arguments of F, you just get F again. And also, if you plug F into the identity that is appropriate there, you just get F again. Okay, so operads are multi-categories with only one object. So if you're familiar with operads, that's one way of thinking of this, is that these are just like multiple object operads. And functors between multi-categories are defined analogously with those for categories. They send objects to objects, morphisms to morphisms in a way that's compatible and is also compatible with the composition and identities. So, well, if we look at this picture, this is basically a diagram telling us how to compose morphisms in a multi-category. But it's kind of special in that the morphisms only go one way, in the sense that if there's a morphism going into, say, C2, then it can't be that there's something that's taking C2 as an argument or something of type C2 as an argument, and then later on giving us something that was one of its inputs, like B1. There's a direction of flow, which normally is just expressed in the traditional paradigm by saying you have a sequence of layers, and the nodes from each layer feed into the nodes in the subsequent layers, at least in the traditional feed-forward setup. And so, well, here's an initial guess at the appropriate definition of an architecture in this paradigm. We could say that an architecture is a multi-category A, where the set of objects is finite, just so that we're not saying anything strange there. And there's at most one morphism in each of the Hom sets. And so this is something like a finite multiple input analog of a poset, because we have this directionality. And so, you know, that's basically the kind of diagram that we draw whenever we draw one of these pictures that's telling us how to plug the nodes of a neural net into the activation functions, which we then plug into others, and so on and so forth. So that seems like a pretty clean description of this type of object. And because we have all of the structure then of a functor category between multi-categories, we have a lot of machinery from category theory that we can try to bring to bear. So as I said before, we can then think of some functor n from an architecture to some multi-category C as a C-valued neural net. And so if C is the multi-category of smooth manifolds, where the morphisms from multiple objects to one are just given by the Cartesian product structure, then such a functor would actually, well, if you chose such a functor to send all objects to just the real line, that's a classical neural network. Each of the activation functions would have to be a smooth map from Rn to R, wherever n is the number of nodes that are feeding into it. And similarly, if C is the multi-category of G sets, also with the product structure there, then such a functor which sent all objects to a single G set as would have to be a G equivariant neural net. So for instance, as I mentioned before, we could choose RK with the action of the orthogonal group, send all of the objects of our architecture of our diagram to that single G set, and then we would get such an equivariant neural net. So that's a nice picture, and it's not that it's wrong. It's not wrong in the sense that like nothing about that like doesn't make sense or isn't reasonable somehow, but there is kind of an undesirable aspect to it, which is the duplication, the thing about the duplication of arguments. So, I mean, I guess what I said is nothing is technically wrong. What I meant is nothing is technically wrong in the sense that if you formally write down everything that I was saying before, it does work, but it's describing something which is a little bit different than what we would normally think of by looking at those pictures. Because, okay, actually, when I wrote down like how I wanted to compose the activation functions way back at the beginning, and I had the H2 of G1 of blah, 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 I was actually duplicating all of the variables that were being plugged in. So we had like an X1, an X2, and an X3, and wherever X2 appeared, that was the same X2, the same value that was supposed to be used throughout that expression. But in a multi-category function, the composition of morphisms doesn't work the way that the composition of like polynomials does. Because if I were to take two things like F1 and F2 here that take two arguments, A1 of type A1 and A2, then when I do this generalized composite, I'm getting something that takes four arguments, a thing of type A1, a thing of type A2, another thing of type A1, and another thing of type A2, and giving me a C, if I want to think of it that way. And so this is a problem for us because that means that if we wanted to use such a neural network to model the type of function I was talking about before, we'd have to kind of duplicate all of those values in our training data in order for this to model the thing that I was actually talking about before, which we could do. It's kind of annoying. And so the idea is we'd really like something that knows to duplicate all of those variables the way that they're supposed to be. I actually want to reuse the same A1 type of thing in my expression and the same A2 type of thing. I don't want to get different choices of them for every one of my activation functions.
It's not enough to use diagonals.
Okay, so then the next thing I'll say is, of course, we could use diagonals. And more generally, I mean, maybe if we decided we wanted to be able to model like multilinear things, for instance, we could say like, well, actually, I want some kind of monoidal category, maybe a prop or some kind of poly category. Like maybe I don't want to be so restrictive as saying that I'm using the Cartesian product or the direct product, but, you know, maybe something more flexible. Maybe I ask that I still have morphisms that play the role of the diagonal, even if they don't actually satisfy like the requisite universal property. But I'm going to propose something slightly different. And I mean, I'm not absolutely married to this, but my hope is that this finds a good balance between what's expressive and what's actually easy to work with. And, if people are interested, maybe I won't go into those comments too much, but at the end, if people want to hear more, I'll talk about like why, I'll give a little more detail about why I think this is justified. Although I will say I'm not 100% at this point. I'm happy to go with something more classical if that's what ends up working, but this is what I've been thinking. So what if we were to do the horizontal categorification of the notion of a clone? So I said before, the things that I wanted to use in these nice examples were polymorphism clones. A clone is just a set of n-ary operations that's closed under generalized composition and contains all of the projections. The projections are enough to duplicate variables because I can project from a list of variables down to a specific one to get a copy of it. The definition of generalized composition for functions in a clone is also different from the multi-category definition. It assumes that you're duplicating the variables that you're plugging in. So we don't have that weird situation that I was talking about here. So in a clone in universal algebra, traditionally, the bottom typing in this bullet point here would be the correct one. You would only have one A1 and one A2, not two copies of each of them. So the horizontal categorification of a clone, which we can't call a clonoid because clonoids are already a thing in computers, in categorical computer science even. But the horizontal categorification, maybe we could call a multi-clone, and it would have a set of objects or a collection of objects. For each tuple of objects, a Ham set just like before. And now instead of asking for identities, I ask for when I'm calling projections, but I'm not assuming have to actually satisfy like the universal property that they do for the product, just some morphisms that are projections, and a generalized law of composition, which is now different from the one that I didn't actually write down for multi-categories, the one that doesn't duplicate variables in the way that I'm complaining about. And the axioms are now that there has to be a generalized associative law, and there have to be some projection laws, perhaps, that are analogous to what the projections usually do. And these are basically some generalization of how the identity is supposed to behave. If you project down to the first variable in the first slot and the second slot and so forth, and do all of that and plug it into F, you'll get F back. And if you take F and you plug it into the projection, you get F back as well. Okay, so I have various reasons for thinking that this might be a nice balance between some different considerations and how we'd like to model these things. But maybe I'll save those for afterwards, so I don't just sort of go off on that. But I'd now like to maybe start to wrap up by talking about another class of examples where we can use polymorphisms of some relational structure as the activation functions for a neural net, and how this perspective might be helpful in dealing with general learning tasks where we don't necessarily know what kind of properties we want to preserve going in. I guess, well, maybe this is a good place to say, are there any shorter questions about anything so far? Okay. So another nice example of another nice family of examples of neural nets comes from graph theory. So we can form a graph if we'd like, whose nodes are k-area relations on some finite set. So just finitary relations of some fixed arity on some finite set. And I can say that two of those relations are adjacent when their Hamming distance from each other is at most 1, or in other words, when the size of their symmetric difference is at most 1, or in other words, when there's a single tuple that lies in one but not the other one. And of course, if I wanted to, I could weaken this a little bit by saying Hamming distance at most 2 or at most 1,000,000, but why don't I stick with 1 for now? So in a recent preprint, I described an infinite family of non-trivial polymorphisms of these Hamming graphs where the arity of the relation is 2, so for binary relations, which can be computed efficiently. And I don't mean anything super strong by this. I just mean that like it's actually possible to code these things and not just like explicitly write down all of their values, through sheer brute force. Although, certainly they probably are easier to compute than a random such polymorphism. And the polymorphisms for Ham and K are going to be pretty similar. It's not hard to generalize. I just didn't explicitly write them down in the preprint that you can find on the archive right now. And so my students and I are experimenting with using these for basic learning tasks using MNIST. So at the moment, we're at the point where we've implemented neural nets that have just generic activation functions, which aren't necessarily like meant to be smooth functions or anything, but we have our own system, which you can see the current progress on GitHub. If you follow the link in the preprint, we are able to implement some algorithm, which I won't discuss right now, and do some basic learning tasks with these. We're still definitely in the process of coding the more involved polymorphisms, which I think will make this a lot more interesting. But we have some decent progress in that. And well, I think that this is actually of broader applicability than just learning things where the activation functions are taking relations as inputs and giving us relations as outputs. And the reason for that is because in my thesis, I looked at a categorification of the notion that Bourbaki gave in their set theory textbook and never used anywhere else in the series of a generalized relational structure. And so I did something more general than this, but I'll just say briefly a special case, which includes any reasonable finite data structure. So what I said in my thesis is something along the lines of consider some index category, which is the script I, and consider a functor taking that script I into the category of endofunctors of set. Well, there is a corresponding functor for any set A, which just takes the index category to set, and that's just done by, well, if this n is just some object of the index category, then you can define this row sub A of n as just being row of n, whatever that functor is, that endofunctor of set, and applying it to A. And so, that is a pretty general thing, but you can imagine, for instance, that row of n might be taking a set A and sending it to, A squared or A cubed, or it might be something like taking a set A and giving us all unordered pairs, so like A choose 2, or maybe giving us the power set of A instead, or any other such thing. Well, we can think of subfunctors of row A, so sub-objects of row A in the appropriate functor category is actually being structures where that row is giving you the signature of the structure. Because if that row of n was like sending A to A squared, that would be like telling us that we had a binary relation if we had a subfunctor for that object. Okay, so there are some other technical details I'm suppressing. You need some assumptions, but given those assumptions, you actually always have a category of such subfunctors of things that look like that row sub A. And that's what I'm going to call the category of row structures, or structures of signature row. And, well, we could consider neural nets where the target category is row structures now. So their activation functions would have to be polymorphisms of those structures. Unfortunately, finding polymorphisms of those things in general is hard if we don't already understand them very well. Even finding one non-trivial polymorphism is NP hard in general. If you just have two relational structures, the existence of a polymorphic or a homomorphism is not an easy thing to do in general. So, okay, that might not be too helpful. But normally, we're not actually given a structure that we want to preserve when we're facing a learning task. Like normally we don't encounter a learning task and we're not told like, oh, there's this nice symmetry that the problem has that you need to observe. In some cases we can tell because like we might notice, for instance, that anything that we want to learn should be maybe multilinear, or there's some kind of algebraic consideration that we know that we need to observe. But in general, that's not the case. We just don't know anything like that. But we are usually given finite data structures as the training data, as in like the actual values that need to be plugged into the neural net often are data that is more structured than just some arbitrary list of real numbers, right? There is often more structure. Like we want to learn something about graphs or about, simplicial complexes or some other kind of structured data, which would be described in the paradigm I was mentioning before, some kind of generalized relational structure. And so, well, the Oneida embedding can actually help us here because we could say, well, if I had, I didn't swap the order here. There's a typo I haven't corrected on this one. Should be, so what I want to say is if we have structures A and C, bold A and bold C, which have some universes A and C, some underlying sets, then it should be the structure, the row structure the row structure morphisms from C to A. I had a transposition that I shouldn't have there. The morphisms from C to A, that's a subset of the set of functions from the set C to the set A. That is a consequence of how I defined structures in the very brief thing that I mentioned before about my thesis. So that's just like saying, like, you know, the set of graph homomorphisms from a graph C to a graph A has to be a subset of the set of all functions from C to A. But if we think about what that's saying we have like a size of C area relation on the set A. And so if we view the Yoneda lemma in that way, then what we're saying, or the Yoneda embedding, what we're saying is that there is actually an embedding from, you know, whether it's graphs or finite topological spaces or some other kind of structure that you would be interested in, there's an embedding from that category into a category, which is what I called struct row to the set. And that's a category whose basic relations are like the ones that I've illustrated here, the ones that you get from the Hom sets. And that's going to be a category whose objects, okay, in general have a proper class perhaps of basic relations, but they're all n-area relations for some n in the classical model theoretic sense. So this is all basically to say that my thesis work, part of it essentially was just showing that if you wanted to look at such generalized relational structures built from sets, that actually you can't really express anything with those that you wouldn't be able to express with just the classical model theoretic relational structures. So the reason that I care about this is because, well, okay, I mean, you could say this first bullet point maybe is a little silly. You could say, well, neural nets then valued in these row structures could actually just be viewed as ones that are you know, that have basic relations, which are just n-area relations in the classical model theoretic sense. But again, that's not really too helpful because we don't necessarily know what their polymorphisms are. But what is helpful is that sometimes we can see that actually for a certain class of relational structures, just a finite number of basic relations suffices. So for instance, if I were to look at unordered graphs, so graphs that undirected graphs, so just simple graphs with no multiple edges, then I could think about that as being like a collection of just unordered pairs, but there is actually a single binary relation in the classical ordered sense that describes that, and it's just the usual one that you would associate with the graph, or the one that has you put an edge going each way in the directed version whenever the undirected one had a pair. And so, well, if you can do that, if you can somehow turn things back into these classical relational structures, then you could actually view those structures as being vertices of some generalized Hamming graph like this. If there was just a single relation, they would be vertices of such a Hamming graph because they would be, say, k-area relations on some finite set. But then by what I've already done, we know polymorphisms of that object. And so we know some kind of nice operations that we can use for activation functions, which take those structures as their arguments and give them as their outputs. And so this isn't like some claim that this is necessarily the best kind of activation function to use for every context, but just that there is at least one kind of universal choice in the sense that will always work. Okay, so not universal in the sense that it's like, you know, somehow covers everything, but just that there is at least a choice of structure that you might want to preserve, and that's given by some of this work in my thesis, which just basically says you can unravel everything into relations and hence into vertices of this Hamming graph. Okay, so I think that is about all that I had. Maybe open it up to questions now.
Well, let's thank our speaker. Thank you very much. Any questions? Any discussion?
I got a question. are we talking about neural nets in the sense of perceptrons, but those would be recognizing these elaborate structures, classifying perceptrons that classify these structures?
Well, I mean, I guess so. What I'm familiar with, here, maybe I'll just go back to the slide on this. So what I'm familiar with a perceptron being is like, okay, so the only perceptrons that I've actually worked with have been just the like doing like binary classification, for instance, in like Rn, right, where you have like a hyperplane and you want to move it around to try to most effectively separate like collections of points that are labeled like red and blue. Right. That's my like that's what I think of when I think of a perceptron.
Okay, then the next level above perceptron would be a neural net in your sense?
Well, I'm just saying that like so a perceptron, I'm not really entirely sure. So I mean, So you can think, I mean, you can think of a perceptron as like determining a function that takes points in Rn and gives you a value, which, you know, if you just discretize it, then it's just saying something like, you know, either 0, the point is on the hyperplane you chose, or 1, it's, you know, it's in one direction of it, or -1, it's in the other direction of it. So I guess strictly speaking, that type of thing doesn't really fall under what I'm saying, in the sense that it's taking inputs of one type and giving you inputs of a different. Oh, no, I'm sorry. I apologize. Okay, it is, because I do allow that. I didn't do that in any of my examples. Sorry. But of course, you could have such a thing. I mean, in the laziest version of this setup, you just let your activation functions just be some functions defined on some sets. And then, I mean, okay, so like in that kind of trivial way, that's a special case. And you can think about formulating it in more or less detail. I wish I could draw, or else I would. Yeah, so you can think of a perceptron just because it's a function that you want to update somehow as being one of these things. There's a degenerate way to think about it, which is to just think of the perceptron, that function from Rn to the set -1, 0, 1, as just being a single activation function.
Yes.
And then there's also more sophisticated ways of thinking of it as being, you know, composed of multiplying and adding the various quantities together appropriately.
Well, I don't mean to be, you know, obnoxious. I'm just trying to get this sense of what level of neural net that you're dealing with. Are you talking more generally about a multi-layer neural net for classifying into multiple bins for inputs, which are these elaborate structures?
Yeah. So like something
like
this. Yeah. So like there might be three bins into which you can throw in whatever kind of objects you want, whether they're structures in the last sense I was talking about, or just, you know, real numbers, whatever. And there are some bins like the D1 and D2 that you actually get the final values out, and you have some multi-layer neural net like this. And so, yeah, I mean, you can certainly model a perceptron as one of these things, but you can also
a real special case.
Yeah, it's a special case, but
so in this diagram here, are we talking about 4 layers? A, B, C, D? Okay, so it's a 4-layer neural net.
Yeah.
Great. Thank you.
Any other questions?
I have a question. Going back to the multi-categories, and then you had multi-categories question mark. That was the modification, is basically to map tuples to objects. Was that the fix?
The fix
when you said that multi-categories aren't quite there.
So yeah, the problem is basically, well, here, let me just go back to the the beginning. Thanks everyone for bearing with me as I'm not able to annotate, which reduces my expressivity a little bit. So if we wait for the slides to update here. So I had said that, well, this picture that is this this diagram that's supposed to represent a 4-layer neural net. Okay, here we go. It looks like it's arrived. So this picture is supposed to represent this function that sends x1, x2, and x3 to this pair, where each component of this pair is some long tortured composition of multivariable functions. And in this expression, the variable x1 appears multiple times. If you were to actually do the corresponding composition with the definition that it has in a multi-category, you wouldn't actually get the same variable x1. You'd get 3 or however many, I guess there are 3 instances. In this expression, you'd get like 3 different copies of something that came from the same object that x1 did. I mean, of course, these things don't have elements in general, but you would have like 3 different copies of an x1 type of thing, for instance. And that's a problem for us if we want to express like this actual formula I wrote down. Like, what if our activation functions were, genuine n-ary functions? This is what we usually mean by such a picture. And so it was actually kind of a lie that multi-categories are the exact thing that you want. It's close, but it's not quite that.
Right. And I'm a little, this is my first time I've heard about multi-categories, but I take it part of the definition of a multi-category as far as the tuples is that like a tuple AB and a tuple BA are the same tuple. Is that correct?
They don't have to be. So saying that the ordering doesn't matter is it is actually an additional condition. Like, it's not
okay. So you're not positing that condition.
No.
Okay.
You can imagine
I wasn't sure if you were or not, because I'm trying to figure out why use like a multi-category versus like like a I guess would be a Cartesian closed category where you can have like currying.
Yeah, or I mean,
currying,
I don't.
Order does matter. Like if you were to like curry functions together, right?
Yeah.
But I'm wondering, like with tuples in particular, if I'm trying to understand, the difference between that and like a category that doesn't have that feature, but that you can do currying to simulate the same effect.
Yeah, I mean, even without the internal hum, like even without being able to curry, like just having products and having the diagonal maps that were also mentioned before would be enough to express something like this. The question is just like, is basically just then like, is that too restrictive? Because there are somewhat natural examples where you might want something that's not the actual categorical product, but some other product. And
yeah,
so
why would you need a rule? Right.
I'm sorry, I missed what you just said.
Yeah, I'm having a hard time hearing.
Oh, really? It doesn't seem like the additional Cartesian closed structure would play any role. I mean, why is it needed? It seems like what you have is the multi-clone category looks like it's enough with projections. That looks fine. So, I mean, in my opinion, it's just an opinion. The example, the geometric example, I guess, would cover things like neural nets that need to recognize objects that might differ. Might need to recognize the same thing if it were rotated or something like this, right? That's the point of using G sets.
Yeah, so people actually do this too. Like, I don't claim to be an expert on equivariant neural nets, but I hope you can see, my goal is just that there should be some kind of nice functorial description of what this general this general paradigm is that people have been exploring, because then instead of this ad hoc kind of, you know, totally organic exploration of the space, we can start to get a little more structure on it to get a handle on what we're collectively trying to study about these things. And category theory is a great tool for doing that.
Wanted to make one comment. About 2 years ago, when we were coming home from a category seminar that Joyal gave, he was expressing concern that he was worried, he was reading about neural nets and saying, yes, this is what you're doing is exactly what's needed in the field.
That's very encouraging. Thank you. Oh, you're muted, No-san.
No, that's all. I just wanted to pass that comment on.
I just wanted to say that the Joyal video is online. You can actually hear him say that.
Oh, cool! I'm really glad to hear that. I did not know about this.
There's a little bit. Yeah.
Well,
go on. Any other questions?
Yeah, I didn't see where learning came into this specifically. We saw a description. We have a descriptive subject, right? I didn't see the dynamics here.
Right. I actually missed that. I did talk about it in my talk at Cambridge, but I actually spaced here. So I just kind of gave this general description, which you can read more detail about in the specific family of examples in the preprint that already exists. So one idea, which is perhaps the most naive idea, I'm not claiming that this itself is like an earth-shattering thing, but one naive idea is to say, choose one of the activation functions in this picture, try changing it to a different activation function, maybe in the same type that you had before. If it was a G equivariant one before, keep it G equivariant. Excuse me, if it was smooth, keep it smooth, whatever, but make some other choice and see if that improves your empirical loss. You know, test that new neural net against your training pairs, see if it does better or worse given your loss function. If it does better, then you should keep that change. If it doesn't, then revert to the one that you had before. That's, you know, and if you want to give an even more detailed description, you can say choose some basic activation functions for each of the arities, the number of arguments that you're going to have it take, and start off with those basic ones, and then choose some unary activation functions, some endomorphisms of the appropriate underlying object that you're looking at maybe, and then you can tweak the n-ary activation functions by composing with endomorphisms in their arguments or in their output in order to get new functions or new morphisms that still belong to the appropriate class. And you could just keep doing this iteratively to try to make progress. Again, I'm not claiming it's super sophisticated, but
what would be your criterion for progress?
Well, so so this isn't something that's, you know, currently included here, although it's possible to incorporate it in the description. Well, okay, I guess you could actually, if you wanted to, try to incorporate this into the actual description that I've given here as well, but it's not, I guess the way I've presented it so far, it's not in the picture, but you can imagine that after you have this last layer of nodes, you then want to evaluate like how good that output is against the, you know, given the inputs that you gave. So you might say like, I want the triple 1, 2, 3 to get mapped to 0, 6. If I plug in 1, 2, 3 and I get 0, 5, I might say, okay, well that's, you know, I don't know, 10% bad, or I'll give some measurement to how far off I think that is from what I'm supposed to get. And so that's called finding the empirical loss of the neural net. And so as long as you have some function that measures the distance between what you think is a correct answer according to your training data and what the answer is that you got currently, then you can use that to measure overall for all of the information that you know that you're training from, how wrong the thing is currently. And your goal is to reduce that wrongness. And the steps I was describing would do that in, you know, perhaps a naive way, if that makes sense.
Thank you very much. It was a very interesting talk and very interesting chat afterwards. Let's thank our speaker again, and we're going to sign off for the semester. And Charlotte, whenever you want to come back and give another talk, you're always welcome.
Yeah, I hope to have a preprint out and have some more detailed information for you before too long. And I'll definitely be checking out that trial video.
Okay.
Yeah, I heard it from a comment in the street, but maybe he put it in the talk as well.
It's a long talk, by the way. All right. Anyways, ladies and gentlemen,
put a link to that talk. Could you put a link to that in the chat, please?
Yeah, no, I can put it in the chat, but you go to the New York City the YouTube page, and he's the most popular talk. So if you sort by popularity, he's the first talk.
Fabulous. Thank you.
It's very easy to find. Anyways, ladies and gentlemen, thank you very much. Have a wonderful evening.
You too.